Bismillahirrahmanirrahim. Electromagnetic field theory, and today our topic is Ampere circuital law. Okay, so let's start with the statement. The line integral of the magnetic field intensity around a closed path equals to the current enclosed by the closed path. Okay, so H dot dl is equal to I enclosed. Okay, so what does it mean? Let's suppose we have a conductor, okay, and the current is flowing through that conductor, so it means it is a current carrying conductor. Okay, so let's suppose I current is flowing through that conductor. Now as the the current carrying conductor produces a magnetic field around it. So for example, this is a closed path of the magnetic field intensity around this current carrying conductor. Okay, so this is a closed path. Okay, now so the line integral, okay, the line integral of the magnetic field intensity around a closed path, okay, means let's suppose this is a small portion dl. Okay, this is a dl small portion. So and the magnetic field around it is h. Okay, so the line integral of that magnetic field intensity is equal to the magnitude of the current flowing through it, means in the current enclosed in this magnetic field ring. Okay, so this is a, for example, this is a 10 ampere. So h dot dl will be equal to 10. Okay, so that is the statement of the Ampere circuital law. Okay, so let's discuss more in detail. For example, we have a long straight conductor and infinite straight conductor. Consider a current carrying conductor extending from minus infinity to plus infinity. Okay, minus infinity to plus infinity. Let the current in the conductor be I. Okay, I is the current flowing through that conductor, and the current flows is in the upward direction. So this is the assumption that the current is flowing in upward direction. Okay, so this is the closed path of the magnetic field intensity around that current carrying conductor. So for example, P is the point of observation. Now the magnitude of the magnetic field intensity through the conductor can be find out by a right hand rule. Okay, so magnetic field intensity generated around it can be find out, the direction can be find out by the right hand rule in such a way that the thumb will indicate towards the current carrying the current direction, and the fingers of the hand, okay, will now indicate the direction of the magnetic field intensity, whether it is clockwise or anti-clockwise. Okay, so and this p point of observation is assumed in such a way that uh, this p crosses the magnetic field intensity ring. Okay, so its direction is in the direction of a unit vector a phi. Okay, the direction of this magnetic field intensity will be the direction of a phi. Okay, so according to s is equal to r theta, s is equal to r theta. So according to this equation, s is actually a dl small portion of the length of the closed path is equal to r. Here the radius is rho, so r will be rho, and for the differential length we have the theta is d phi. Okay, although the complete angle is from 0 to 2 pi, but for the differential length the angle is, for example, d phi. If we consider a whole ring, okay, then this will be from 0 to 2 pi. Okay, so this is the later case. Now we are assuming the dl, the differential length. So in this case dl is equal to rho d phi. Okay, so h is equal to h in the direction of unit vector a phi. In order to find the magnitude of the magnetic field intensity at point P, consider a closed path, and that closed path must passing through the point P having a radius of rho. Okay, so the point P having radius rho. Now consider a very small segment of the circular path, and that is dl. The magnitude of this differential length vector is rho d phi. I have explained it over here. S is equal to r theta, so r is rho theta for the differential length will be d phi. Okay, so dl will be equal to rho d phi and is along the unit direction a phi. This is also along the a phi. So now, according to the Ampere circuital law, the integral, the differential integral of the magnetic field intensity is equal to the current enclosed by that um, integral path. Okay, so now the complete path, the limits will be from 0 to 2 pi. So 0 to 2 pi h in the direction of a phi from here, and dl is equal to rho d phi, and this is also in the direction of a phi. So multiplying these two, there will be a dot product of these two unit vectors, a phi dot a phi, which is equal to 1. So we will get I is equal to h rho d phi. Now applying integration, so integration for the phi will be from limits varying from 0 to 2 pi. So we will get 2 pi minus 0, which is equal to h rho 2 pi is equal to I. Now this is the value of the current. Now in order to find the h value, okay, so h will be equal to I divided by 2 pi rho. Okay, so this will be the value of the magnetic field intensity according to the Ampere circuital law. Okay, so remember this equation, we will use it again and again in the upcoming topics as well. Okay, especially for the coaxial cable we will use this equation, so keep it in mind. Okay, so now move to the next slide. H is equal to I over 2 pi rho. Okay, so now coaxial cable, we have already discussed about the coaxial cable in the midterm course as well. So now again, coaxial cable as application of Ampere circuital law. So as we know that in coaxial cable we have two conductors. The one is the inner conductor and the other is the outer conductor. The inner conductor is the solid conductor. Okay, so but while the outer conductor is in the shape of the hollow conductor, just like a pipe. Okay, so we will have two surfaces for that outer conductor. Okay, so this is the inner surface of the outer conductor and this is the outer surface of the outer conductor. So now considering the radii for all of these surfaces, so from the center to this inner conductor wall, this will be equal to a is the radius for the inner conductor from the center, and now b is the conductor of b is the radius of the outer conductor, the inner surface of the outer conductor, and c is the radius of the outer surface of the outer conductor. Okay, so A, B, and C. Now we have to consider a point of observation for at different points. Okay, before this, first we will cover we will know about the current density. Current density is actually the current flowing through a unit area. So as we have two conductors, remember that the current direction in these two conductors will be opposite to each other. Okay, so for example, if the current through the inner conductor is in the upward direction, then the current through the outer conductor will be downward direction. Okay, so these two are in opposite direction. Okay, now the current density. Okay, so J is equal to current flowing through the unit area. So J for the inner conductor and J for the outer conductor. Okay, so according to this formula, area for the inner conductor pi r square. So for the inner conductor, r is equal to a, so that is why the area will be pi a square. Okay, for the inner conductor, pi a square. Now the effective area for the outer conductor. Okay, actually this is the hollow conductor, so we will consider the effective area for this shaded region only. Okay, so this is actually b c minus b. Okay, outer uh, surface minus inner surface for the outer conductor, so c minus b. So by this way we will have pi c square minus pi b square. Okay, so taking pi as common, pi into c square minus b square, this is the effective area of the outer conductor. Now j naught and j naught and j naught will be equal to I over pi into c square minus b square. Now considering different the point of observation at different points. So first of all, we will consider the point of observation in between a and b, that is greater than a and less than b. So locate that point. Where is the, it will be the location. So I will take the green color. Now this is the first point of observation. Okay, that is greater than a and less than b. Okay, so we will consider an imaginary closed path around this. Okay, so applying the Ampere circuital law, ACL Ampere circuital law, H dot dl is equal to I. Okay, so H is equal to H in the direction of a phi, dl is equal to from S is equal to r theta. This is also equal to rho d phi in the direction of a phi. Dot product, this will be equal to 1. We will get H over H is equal to I over 2 pi rho. We have already derived it in the previous slide as well. Okay, so this is actually the value of the H when we will have the point of observation in between A and B. Okay, now if you have the point of observation greater than C, means you will have point of observation over here greater than C. Okay, this is now the point of observation. So what will happen, we will consider a closed path. Okay, so the current enclosed in that closed path is equal to 0, because the current enclosed in that region is equal to I minus I, the current flowing in the upward direction and the current flowing in the downward direction. Okay, so both have the same magnitude and different directions, so that is why I minus I is the total current enclosed by that surface. Okay, so that is why it is equal to 0 when we will consider a point of observation greater than C. Okay, remember that the radius for inner conductor is A and B is the outer inner surface for the outer conductor, C is the outer surface for the outer conductor, but the radius for the point of observation will be always rho. Okay, in this case we will have rho is the radius for from the center to the point of observation. Similarly in this case we will have rho. Okay, so now considering the point of observation at some other point, a rho is less than a, means we will have point of observation somewhere here less than a. Okay, so only the inner conductor is involved in that case. So H according to Ampere circuital law, H dot dl is equal to I enclosed. Okay, so I enclosed is also equal to this according to definition of the current density. So J dot cross means multiplication of pi rho square. This is the radius for the point of observation. Okay, Now Ji is equal to I over pi a square. This is the current density for the inner conductor. We have already discussed it in the previous slides. This, okay, the current density for the inner conductor, okay, I divided by pi a square. So I divided by pi a square into, this is the area for the point of observation, okay, area of the radius, area of the path for the point of observation means this one, okay. For each point of observation we have to draw an imaginary closed path around so that it crosses that p point. So ji multiply by pi rho square, pi will be cancelled out. So we will get I rho square over a square. Remember, this is the value of I. Now according to Ampere circuital law, H dot dl is equal to I enclosed. I enclosed is equal to I rho square from here divided by a square, okay. So I have already told you that we will use this equation again and again, so you have to keep it in mind at any time. So according to this, J dot dl is equal to pi HL is equal to this one, okay. This is actually the integration and the limits of the complete dl from 0 to 2 pi. So by this way we will get 2 pi minus 0 to pi h rho is equal to this. So this is the h value for the point of observation less than a, okay. Now the fourth case, for example, we will have a point of observation somewhere in between B and C. So where will be that location? That location will be here, okay. This is actually in between B and C, okay. this this location, okay. So we will consider a imaginary closed path around this that crosses this P. The radius for this will be rho, okay. So now uh, I enclosed in that region is both the current is involved, I, okay, this and this as well, okay. So I in plus I out. So for example, I outer from the outer conductor is equal to minus J naught. Minus is because of the current is moving opposite to that, that is the current flowing in the inner conductor. So if the inner conductor is positive, so the current flowing through the outer conductor will be negative, okay. In this case the I minus n I is not equal to 0 because the complete the conductor is not considered. We are limiting to this region only. So when we have the point of assertion greater than the C, in this case I minus I is equal to 0, okay. Now a partial conductor is involved, so we cannot say that I minus I is equal to 0. Rather we will find the separate current for the outer conductor. That is the current for the outer conductor. I naught is equal to minus J naught pi rho square minus B square, okay. B is involved, okay, because C is greater than the rho. So C will not be counted in this case, only B will be counted. So I naught is equal to minus J naught pi rho square minus B square, okay. So by this way, putting the values for the J naught, this is the value for the J naught. We have already found in the previous slide, I over the area of the outer conductor, okay. So pi square C square minus B square, and this is the area for the closed path of the point of observation. So pi will be cancelled out with pi, you will get this. This is the I naught. Now putting these values over here, you will get I in is, for example, I, and I naught is equal is also this I times this one, okay. So taking the LCM, we will get this for the I enclosed. Now applying the Ampere circuital law, because we are using the coaxial cable as an application for the Ampere circuital law. So Ampere circuital law is mandatory at the end of each step. So H dot dl is equal to I enclosed. H dot dl is equal to, for the complete path, this is equal to this, and I enclosed, we have find I enclosed here. So putting the I enclosed over here, so we will get H is equal to I over 2 pi rho. Okay, we will divide 2 pi rho on both sides, so this will be shifted over here, I over 2 pi rho, and c square minus rho square over c square minus b square. This is actually the H for the case if we have the point of observation in between B and C. Okay, so that is all about the Ampere circuital law. uh, Thank you.